Hi, welcome to this lesson on Probability Counting Principles Part 2. Let's have a look at question 6. The standard 13-digit South African ID number was formed as follows. The first 6 numbers indicate the year, month, and date that a person was born. The next 4 digits indicate gender, where 0001 up to 4999 represented females, and 5002 9999 represented males. The next digit indicates the country. Were you born in South Africa, then you were given a 0. If you're not born in South Africa, but you become a South African citizen, then you get a 1. The second last digit is a standard 8 for everybody. And the last digit verifies the ID and is used as a control number. We can assume that the last digit is a randomly generated digit from 0 to 9. So there are 10 options here. And that leap years can be interpreted as people being born on the 28th of February. So, the first question asks us to calculate the total number of possible ID numbers. So let's break it down logically into what is actually happening. So there's going to be a case-by-case basis. What do I mean by that? Well, first of all, we're going to have 6 numbers for the first indicating year, month, and date. Then the next 4 digits depending on gender. And then 3 digits where this second last one is always an 8. So there's only one option here for everybody. Okay, the last digit goes from 0 to 9. So there are 10 options here for the last digit. And then this digit here is country, South Africa 0, or not from South Africa 1. So there are 2 options here. You're either born in South Africa or you are not born in South Africa. Okay. Now, in terms of the gender, it starts from 0001 all the way up to 9999 and is partitioned between females and males, but the collective group altogether, there are 9,999 total digits that could go here for that gender position. Now, this is where it gets a bit nuanced, because now we've got to think carefully when we count. Okay, because this is essentially counting principles. Now, if we list out the months, so you have January, February, March, April, May, June. Okay, then you have July, August, September, October, November, December. January has 31 days. February will assume 28 days, and with a leap year on the 29th, we'll assume still that we'll give the birthday on the 28th. That's why we were given that information. Okay, March has 31 days, April has 30 days, May has 31 days, June has 30 days, July has 31, August has 31, September 30, October 31, November 30, and December 31. Okay, so that's important when we count, because when you think of the years now, remember it's this very last 2 digits of the year. So now, think of the years that could happen. Someone could be born in the year 1991. Someone could be born in the year 2000. Someone could be born in the year 3576, if we ever get that far, right? But essentially, if you're looking at the last 2 digits, they can range from 00 all the way up to 99. So in total, there are 100 different possibilities from 00 to 99. And then when we get to months and days, well, now these will depend on the month that we are looking at, okay? Because certain months have 30 days, certain months have 31 days, and only one month has 28 days. So to get the total number of possible IDs, what's common to all of them are these 100 for the years, the 9999 for the genders, 2 for the country, 1 for that 8 digit in the second last place, and then 10 options for the control digit. That's what they all have in common. Now, we need to consider the cases of the 31 days, of the 30 days, and the 28 days. Okay, and why am I multiplying is because this is going to be multiplied into the 31 days, and then we're going to add it to the case of the 30 days, and then we're going to add it to the case of the 28 days. I'm just doing that algebraic manipulation at this point, whereas if I decided to write out all the different cases and I add them all up, I'm eventually going to take out this common factor at the end. So that's what I've done now. Okay, so for 31 days, how many are there? There's 1, 2, 3, 4, 5, 6, 7. So 7 months have 31 days. Okay, because there will be, for the month here, 7 different months and 31 days. So by the fundamental counting principle, you'd multiply. Then for the 30 days, there are 1, 2, 3, 4 days. So 4 months have 30 days. And only 1 month has 28 days. Okay, so let's go ahead and do that calculation and see what number we end up getting. Okay, so the common factor we took out, so let's just bring it up here. It's going to be 100 times 9,999 times 2 times 10. Open bracket, 7 times 31 plus 4 times 30 plus 1 times 28. Now, before I hit enter, let's think about this realistically. We would like enough ID numbers so that we never end up with the problem that there are more people than there are ID numbers, because then what happens once you reach that limit? What will the people after that have as an ID number? There can't be a repeated ID number. You've used them all. You can't give an ID number to someone that already has that ID number, right? Because if you look that up on a database, for example, wherever now that one ID could have 2, 3, 4 people attached to it, how do we know who we're talking about? The whole purpose of an ID number is to identify that unique person. So it should be quite a big number. As of recording, there's around 60, maybe even growing potentially to 70 million people in South Africa currently. So we would definitely want enough ID numbers that go past that number. So let's press equals. Wow, huge number. That is 7,299,270,000. 7,299,000,000. And let's just go back there and check the last few numbers again. 7,299,270,000. That is, well, used to be very close to the population of the entire planet, right? Because as of recording, there's just over 8 billion people currently on planet Earth. So that definitely means we have enough ID numbers in future cases for more people that become South African citizens. So we are definitely safe enough right now, okay? And I doubt that you could potentially put 7 billion people into South Africa alone. Geographically speaking, I don't think we can probably fit that many people, but I might be wrong. But yeah, so that is definitely more than enough ID numbers that we could assign to people. Almost enough for the entire planet if they were South African citizens. Okay, now what is the probability that a randomly generated ID number is of a South African female born during the 1970s? So now we have some restrictions. So the number here is going to be smaller than the total number. So first of all, let's set this problem up. I'm first of all going to say that the probability of SA female born in the 70s, that's going to be the number of people that were born in South Africa that are female at birth and that have been born in the 70s, divided by the number of people in total. Okay, so let's go ahead and work out. So there's two ways we can go about it, right? We'll do a full logical breakdown of it, and then we'll see what happens when we simplify the problem a bit. Okay, so if we do it fully logically, what do we actually have here? So we know the total number of people. It's this number here, 7,299,000,000. So 7,299,000,000 and 270,000. Now we want the person to be from South Africa, be a female, and be born in the 70s. Okay, so let's logic this out. So we have 6 places here, 4 places here, 3 places here. Again, this second last digit has to be an 8, so there's only one way. Okay, so we want them to be from South Africa, we want them to be female, and we want them to be born in the 70s. So for the year case, they can be born either 1970 all the way up to 1979. So there are 10 years between 1970 and 1979 we can choose from. Okay, so there are 10 possibilities here. And now we weren't told which month or which month they were born. So that'll depend, whatever month they were born in, the days will also depend as well. So we'll leave that for now. We're also told that they are a South African citizen. So that means that this digit must be a 0. So there's only one option here. And then the last digit is a control digit. So that's still 10 possibilities here. Okay, so that just means there are 10 possibilities there. Okay, then being female means that you are represented from 0001 to 4999. So there are 4,990 different possibilities here for the female option. So essentially, the numbers that we are going to be interested in is the month and the day the person was born. So the numbers that are common are 10 times the 4999 times the 1 times the 1 times the 10. Okay, those were these number options here. Then again, I'm going to do a similar logic to this piece above here, where we look at what month they were born. So if they were born in any of the 7 months, then there were 31 days there, or the 4 months with 30 days, or the 1 month with 28 days. So we can work out this number, and then that'll be the total number of South African females born in the 1970s. So let's bring up our calculator. So the common term was 10 times 4999 times, well, I'm not going to put the ones because that doesn't do anything. 7 times 31 plus 4 times 30 plus 28. So I get 1,824,000. Well, let's actually read that there. So there's 3 zeros, 3 zeros. So it's 182,463,000. 182,463,000. And what were the last 3 digits? 182,463,500. Okay, so that's 182,463,500 unique ID numbers for a female that was born in the 1970s and was also born in South Africa. Okay, so that's the total number. So let's go ahead and put that in. So that's 182,463,500. Okay, so we take that number now and we divide it by the total number. Okay, and then we're going to get, so divided by 7,299,270,000. That's going to give you 0.02499. So if we round off to, let's say, 3 decimal places, it'll be approximately 0.025. Okay, so that means there's almost a 2.5% chance of finding someone who is South African born, female, and was born in the 1970s. Okay, so that was the logical way. But if we just focused on the key variables, which was country, gender, and year, then we could have also simplified the problem as follows. So the same probability value would essentially be just looking at the criteria for these 3 divided by the total criteria in general. So what do I mean by that? Well, let's see. So let's put out our 13 digits again here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. And then 1, 2, 3. Let me just bring those a bit closer. Okay, so let's put them here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, and 1, 2, 3. Okay, so if I'm just focusing now on the country, gender, and year, I'm not worried about any of the other variables. Okay, so for country, it was in this digit. Okay, so now if we look at our specific case, it is South African, female, and 70s. So how many of those in total? Well, for South African, there's only one option between the 0 and the 1. It's a 0 for South Africa. Okay, for years, okay, of the 1970s, there were only 10 different possibilities from 1970 to 1979. Okay, so we've done country, we've done year, and then gender for female we saw was 4999. So by the fundamental counting principle, it's going to be 10 times 4999 times 1. So that's for that specific case. Then the general case is any country Well, it could be 0 or 1. So there are 2 options for the country. Then it could be any gender. So from 0001 to 9999, there were 9,999. And then for year, it could be any year. And we saw that there were 100 possibilities for the years. So if I do this calculation now, does it give us the same answer? Let's check. So it's going to be, in the first case, 10 times 4999 times 1. And then in the bottom case, it was 100 times 9999 times 2. And we can see we get exactly the same answer. So 3 decimal places there. Okay, so those are the 2 different ways we could have done this, through pure logic or by reasoning and simplifying the problem down to the specific variables that we were looking at. All right, I'll see you in the next one.